All right, today we're looking at assignment 41, and we're going to do problem D, which is one of the ones from the back of our chapter in our textbook. So remember, you can always look at the solutions to the problems in the textbook. So this problem has a couple of parts, and as always, I think it's best to write down your given. So it says flywheels are large, massive wheels used to store energy. They can be spun up slowly, then the wheel's energy can be released quickly to accomplish a task that demands high power. An industrial flywheel has a diameter, so they're giving me the diameter of 1.5 meters. Now, most of our equations have radius, so the radius would be half of that is 0.75. It has a mass of 250 kilograms. Its maximum angular velocity is 1200 RPM. So we're not going to actually write, so that's omega. And since it starts from rest, omega naught is 0. So omega F is 1200, but we're not going to write RPMs. We're going to write it like a unit, revolutions per minute, like this. Now what we're going to do is, we know we're not going to do revolutions per minute, so we're going to convert. So if I have revolutions in the numerator, I put revolutions in the denominator, and there's 2 pi radians per revolution. I have minutes in the denominator, so I put minutes in the numerator, and 1 minute is equal to 60 seconds. So now I see easily that this revolution cancels with that, and this cancels with that. So when I do all this on my calculator, it comes out to be 125.6 radians per second. Now I'm going to continue to read the problem. So for part A, it says a motor spins up the flywheel with a constant torque. So the torque is equal to 50 newtons times a meter. How long? So when it says how long, I want to find the time. Does it take the top flywheel to reach the top speed? So I already know the top speed, omega F. I know omega naught is 0. They want me to find time, so obviously what I need is, I need alpha, the angular acceleration. So I'm going to be using angular kinematics to solve for alpha, but before I do solve for t, I have to solve for alpha. So I'm going to look back at what they gave me. So they gave me the torque is equal to 50. So I know that torque is equal to I alpha. So I know alpha is equal to torque over I. Now, one of the things I noticed I didn't do is, I should have done in the beginning, the flywheel's a cylinder. So what I should have done right off is, I should have found the moment of inertia. So I is equal to 1/2 mr squared. So it's 1/2 of 250 kilograms times 0.75 meters squared. So my moment of inertia comes out to be 70.31 kilogram per meter squared. So now I can go back and substitute this in here. So this is 50 Newton times a meter divided by 70.31 kilogram per meter squared. So remember, a Newton is a kilogram meter per second squared. So if I want to carry my units out and cancel them, kilogram meter per second squared times a meter, that's all this, over kilogram per meter squared, I see that my angular acceleration comes out to be 0.711 radians per second squared. So now I can take this value and substitute it in here. So now I found this, I have this, I have this, and I want to find that. So the equation I'm going to use is omega F is equal to omega naught plus alpha t. So omega F minus omega naught over alpha is equal to t. So 125.6 radians per second minus 0 divided by 0.711 radians per second squared. So the time comes out to be 177 seconds. So that's part A. For part B, it says how much energy is stored in the flywheel. So again, we're always thinking about the rotational analog. So kinetic energy is kinetic energy. So we know kinetic energy is 1/2 mv squared, but this flywheel's rotating about an axis of rotation, so it's 1/2 I omega squared. So it's going to be 1/2 of 70.31 kilogram per meter squared times 125.6 radians per second squared. So when you do it on your calculator, you get a big number, 554,582.8, but we're going to put it in significant figures, so 5.55 times 10 to the 5 joules. Part C says the flywheel is disconnected from the motor and connected to a machine to which it will deliver energy. Half of the energy is stored in the flywheel is delivered in 2 seconds. What is the average power delivered to the machine? So we know from before that power is equal to work divided by time. Now remember, work is equal to the change in energy over time. And this time they want half the energy. So we're going to use half the energy from part C. So it's going to be 1/2 5.55 times 10 to the 5 joules divided by the 2 seconds they told me. So when I do all that on the calculator, I get 1.39 times 10 to the 5 watts. And then the last part, part D, it says how much torque does the flywheel exert on the machine? So I want to find the torque. So I know torque is equal to I alpha. We already know the I, so that's easy. But now we have to find a different alpha. We're now finding the alpha that was half of the kinetic energy. And we also have a different omega. So what we have to do is, first, I'm going to find the omega. So when I rearrange this, this is going to be omega F is equal to, well, I skipped a step. Let's go backwards. I know that kinetic energy is 1/2 I omega squared. So now we want to find this omega. So I'm going to rearrange this equation, and I'll multiply both sides by 2. I'll divide both sides by I, so 2k over I is equal to omega squared, and then I'll take the square root of both sides. So omega is equal to omega F is equal to omega naught plus alpha t. So we're going to rearrange this equation. So omega F minus omega naught over t. So this alpha is going to be, so we're going to do the full energy minus the half energy. So we're going to do 125, what we got up here, 125.6. So this is the full, and this is the half energy. 125.6 radians per second minus 88.85 radians per second divided by the 2 second interval. So now the alpha comes out to be 18.38 radians per second squared. And then once I get this, I'm now going to substitute it back in this equation here, that torque is equal to I alpha, and I'm going to solve for the torque. So the torque is equal to I alpha, so that's equal to 70.31 kilogram meter squared times 18.38 radians per second squared. So my torque comes out to be 1292 Newton times a meter. So this lesson really isn't that difficult. The only new thing that we're doing in this lesson is that the rotational kinetic energy is equal to 1/2 I omega squared. So when you go back, there's a lot of places you can make a little mistake. So the first thing is you want to write down your given. So again, they gave me the diameter, not the radius. I'm always using the radius. They gave me omega f in revolutions per minute. I want to convert that to radians per second. I have to say what its shape is a flywheel. A flywheel is like a cylinder, so I'm going to do the moment of inertia of a cylinder. Then as I write stuff down, I'm going to say, okay, here torque is equal to I alpha. I want to find alpha. I was given the torque. What do I need? I need the something else. I need my alpha. So I'm going to go back and I'm going to say, okay, what do I need to do to solve this problem? So I do everything step by step. When I do it step by step, write down, the more you write down on paper, the less likely you are to make a mistake. So it's not so bad. And that's it.